it. My lovely fractal. Hey there, I'm David. I'm the coordinator of the Maths Learning Centre. It's semester 1 2018, and this is the revision seminar for Maths 1B. Hello from the past, those who are watching in the future. Okay, and hello to you guys, but we've covered that already. So, I've got several requests and I'm going to deal with them in no particular order. So I might have a look at the first one that's on my list and do that first. So we have linear transformations. And in particular the kernel and the range. Okay, so quick intro to what linear transformations are so that anyone who's watching this in the future before they get up to this topic will know what we're talking about. So, we've seen functions before. I mean, we've been looking at functions since about year 9, and where you put numbers in and they spit numbers out. And now, here we are in Maths 1B, and we are now looking at functions that take vectors in and spit vectors out. And there are any number of functions like that that you could imagine. And they don't even have to spit vectors out, they're allowed to just spit numbers out as well. Any number of functions that you could imagine like that, so you've seen lots of them before. You can take a vector and you can calculate its length. That's a function that takes a vector in and spits a number out. You could take a vector and rearrange its coordinates, put the last one first and the first one last, and that would be a function that takes vectors in and spits vectors out. And you could take a function and you could square all of its coordinates if you wanted to, and that would take a vector in and spit a vector out. You could do any number of things with a vector, but we're specifically interested in the nicest possible nicest possible functions, which are called the linear transformations. And the linear transformations have this wonderful properties that they preserve the things that we care about vectors. So vectors do linear combinations, they do addition and scalar multiplication. And what we're going to do is we're going to have a function that preserves that. That's what they do. So the definition is that a linear transformation f which sends r something into R something doesn't really matter what the letters are. Linear transformation when, if you do a scalar multiple first, it's the same as doing the scalar multiple afterwards. And if you do addition first, it's the same answer as doing addition after for any U and V in Rn. So that's the definition. It's important to be able to remember what that definition is, because if you ever have to do a proof that something is a linear transformation, then you must use a definition, because proofs, that's what you need to do. You have to use definitions in proofs. So in my head, I remember it saying that, well, vectors are only vectors because they do addition and scalar multiplication, and linear transformations preserve that. So you can essentially bring constants out and you can expand them out over addition, and that's a linear transformation. Cool. But the big idea in linear transformations is that no matter which linear transformation you care to name, it's possible to rewrite it as matrix multiplication. So there's totally a theorem, I don't know what it's called, but I will just call it the truth. I don't know what the theorem is called. Any linear transformation can be rewritten as f of vector is A times vector for some matrix A. And in fact, actually it's not just some matrix, it's for exactly one matrix. There's only one way to actually do this. And that matrix is called the standard matrix for the linear transformation. Can I fit this in? Standard matrix. Now, why would you call it the standard matrix as opposed to just the matrix if there's only one? And the answer is that, well, there's only one way to do it if you use the coordinates for vectors that you have, but if you change your coordinate system into a different system of coordinates, then you'll have to get a new matrix. So this is called the standard matrix because it's the matrix that goes with the standard coordinate system. Just so you know, if you ever study Algebra 2 in the future, then you may learn non-standard matrices for linear transformations as well. But I like to tell you why the words are there. Otherwise, you could just call it the matrix because there's only one. Okay. So this is a big idea. It's a little bit like in Maths 1A when subspaces turned out to all be the span of something, even though you could define them in different ways. And so today, linear transformations turned out to all be, you know, we went, oh, if we multiply by a matrix, that does what a linear transformation does. I can expand that out of a plus. I can bring out constants. That's great. And it turns out that every linear transformation can be rewritten that way. But it might not be written that way to begin with. Cool. Right, we're nearly up to it. So that's great. So that means that things about linear transformations become things about matrices and vice versa. But because matrices and linear transformations were thought of independently, and only later we discovered that they were the same thing, when you're talking about linear transformation, you use different words than when you're talking about a matrix. There you go. So there are things that we would like to know about a linear transformation and things that we would like to know about a matrix, and they are the same thing. So let's see. The range of a linear transformation is the set of all the vectors that come out. And that's the same definition of the range of any function that we used to do before. I mean, for a function, the range, ordinary function of numbers, the range was all of the numbers that came out. But for a linear transformation, it's all the vectors that come out because that's what it produces. Okay, that's how I think it in my head, all the vectors that come out. And the definition is that the range of a linear transformation f is the set of all vectors y such that y is equal to f of x for some x. Okay, so this is saying that it's all the things y that came out of the function, because f of x means it came out of the function. That's the definition of the range. And you can define that range even if you don't have a matrix yet. You can always find a matrix if you want to. And the range, that's great. And so it turns out that lots of linear transformations don't cover all of the space that they're going to. So the picture in my head, everything in more dimensions than 2 is a blob. And so here is Rn. And here is Rm. And the idea is that if I track where all the points here end up in Rm, so maybe this one goes there, and this one goes there, and this one goes there, and this one goes there. And if I do it for all of them and collect them all together, then the thing that I make, that's the range. That's the picture in my head. And it's technically possible that you can cover the whole of Rm. And it's also possible that two different vectors may end up in the same position. That's fine. It just means that we collect together everything that it can produce, and it may or may not cover the entire of Rm, but whatever it does cover, that's called the range. Okay, that's what a range is. But if we're looking at a matrix, it's called the column space. So, linear transformations have ranges, and matrices have column spaces. It's not technically correct to say that a matrix has a range, and it's not technically correct to say that a linear transformation has a column space. Column space is a word that goes with matrices, and range is a word that goes with linear transformations. And so the definition of this is that it's the set of all the linear combinations of the columns. So the definition of the column space of a matrix is A1 Vn such that A1 up to An are in R, and where V1 up to Vn are the columns of A. Well, I suppose, we don't have to say it that way. We can just say the span of V1 up to Vn. That's an alternative way of saying it, which is just as good and shorter, so therefore actually better, because this is what span means. And actually, because it's a matrix, I can actually rewrite it in a different way. I know that doing linear combinations of a matrix is the same as multiplying them by a column vector, because when you do a column vector, it does a linear combination of the columns. And so this is the same as saying all the things that come out if we do matrix times x for every possible x, then that will produce the column space. So this one's the definition. That's the definition. And this also happens to be true. The thing that's really useful, this one here, is that's useful for doing proofs with. Okay, and that's just a mechanism of about the way matrix multiplication works, is that matrix multiplication by a column is the same as doing a linear combination of the columns. And this one's nice because this one matches with this definition here. If I do all of the fx's, and f of x is the same as a times x, then that's the same as this. All right, cool. So the range of a linear transformation is the same as the column space of the matrix, the standard matrix for the linear transformation, but one of them's thinking about it as a function, and the other one's thinking about it as a matrix. All right, so what's the next thing? Kernel. Okay, so the kernel of a linear transformation is what you used to do with ordinary functions, where you figured out where they cross the x-axis. So when you take a polynomial and you find its zeros, what you are doing is you are finding the kernel of that function. So we used to be really interested in finding out when functions came out to be zero. And we still are, and that's what the kernel is. So the set of all vectors that produce 0. I've underlined it because it's a 0 vector. So the definition is that the kernel of a linear transformation is the set of all x's in N such that f of x comes out to 0. Sweet. So you'll notice that actually these two linear transformations, well, I'll notice, these two functions these two sets are described in opposite ways. The kernel is described, the rule for being in the kernel is that the equation comes out to 0, that it satisfies this equation, and the rule for being in the range is that it's possible to write it in a certain way. And they're the opposite ways. In fact, they're the two opposite ways of writing a subspace. A subspace can be written as solution to equations, or it can be written as the span of something, and the kernel and the range go with those two options. So in terms of the picture I drew before, now it looks like you always go from a bigger Rn to a smaller Rm, but that's not always true either. I wanted them to be different sizes, so I had to pick a different size. So the idea is that I actually now collect together everything here that ends up at 0. I'm going to use a different colour so they don't get mixed together in people's minds. So I might find all the things that end up here at 0. Collect them together, and that's the kernel. So when we do the kernel of a polynomial, we just get a collection of dots. And when we do the kernel of a straight line, we just get a single number. When we do the kernel of a linear transformation, we get, this blob, whatever it is, and we'll talk about that. And so the null space of a matrix is that same idea, but when it's a matrix and not a linear transformation. And so this is set of all the solutions to AX equals 0. I mean, there's no other way of saying it. So it's all the vectors that when you multiply them by the matrix end up at 0. If you think about them, they're the ones that make the matrix 0. That make the matrix do the same thing that 0 would do. So the null space of a matrix is the set of all x's in Rn such that Ax is 0, which is extremely similar to the way the kernel was written. It's just that instead of f of x, we've just written A times x, which makes sense if that's what f actually is. And there's no other real way of writing it than that. Like, you just have to solve the homogeneous system, and that is that. So if you like, all right. Cool. That's pretty much the deal of what they are. I'd like to do some comparisons here. So some comparisons.
Should you not define that the A matrix is not the 0 matrix?
Oh, well, no, we're saying we have an A matrix to begin with.
Oh, okay.
So someone gives you a matrix and you say, oh, I have a matrix, I can find its null space. Yeah. If the A matrix is the 0 matrix, then everything is in the null space.
Yeah.
That's an important question. Well done. Yeah, so you're right. The A matrix doesn't have to be the 0 matrix. It could be any matrix at all. And every matrix has its own null space. And the only matrix where the entire of Rn is in the null space is the 0 matrix. So that's a good thing to say. I might even say that. Every matrix has its own null space. So it's possible for two matrices to have the same null space but be different matrices. If you pick two different matrices, it's usual that they have different null spaces. Cool. Yeah, anyway, we'll get to that in a minute. Okay, so I just want to compare these two things for a second. These two pictures. An important thing that helped me focus when I was doing questions on this is to realize that when my linear transformation goes from here to here, the kernel lives in the start space and the range lives in the end space. And what that usually means is the kernel has made of vectors with a different number of coordinates to the things in the range. And I'll do a proper example so that we can get a handle on how all this works in a second. But that's something that I used to hold on to. The range lives in the finishing space and the kernel lives in the beginning space. In fact, the kernel is inside here, and it's just that it only ends up being this single dot in this picture here. So this picture is sort of inside this picture. All right. Time for some examples, because that's what you really want. Okay. And I will do an example of doing composition of them for whoever added that to my list in a minute. Okay, so some examples. Find the kernel and range for f, which sends, I'll fill that in a second, where f of x, y, z is x plus y, 2y minus z. Okay. I'm just going to write something here in a second. So when I look at this, the things that I put in have 3 coordinates, so they are in R3. And the things that come out have 2 coordinates, so they are in R2. So that's what it means by going from R3 to R2. I'm just doing some random calculation on the coordinates of this thing. So there are 2 ways to approach this, and I'm going to do them both. Okay? So that you can compare them, and so that you have 2 things to try when you get to your exam. So one way is to just do it direct, using the definition of what kernel and range are. So let's see, the kernel of f is the set of vectors that come out to 0. So it's a set of x, y, z's such that f of x, y, z is the 0 vector. And it's a 0 vector in the appropriate space. It's in R2, so it has to have 0, 0. Okay, that's the definition of what the kernel is. And so what I need to do is I need to solve this equation. But f of x, y, z is x plus y, 2y minus z, which is 0, 0, which means what I'm solving is these equations. So I've just said, well, this coordinate has to be 0, and this coordinate has to be 0. Ta-da! And now I have 2 linear equations to solve, and I will solve them. So x and y, 1, 1, 2, whoop. 0, 2, minus 1. Got myself caught there. There were only 2 columns here, and so I thought it was a 2 by 2 matrix, but it's not. It's got an x and a y and a z, so I need to line them up with their appropriate coordinates. So x, there's 1 x and 1 y here, and no z's. And here there's no x's and 2 y's and minus 1 z's. Important pitfall to keep in mind when you're doing these things. And that's why I always write down the unknowns that I'm trying to solve for. Okay, so that's not too bad. It's almost in reduced row echelon form. I mean, we've got a 1, 0 here. There's absolutely nothing stopping me from putting my second column of the identity matrix wherever I want. So traditionally, you find the reduced row echelon form. So traditionally, you go, you put a 1 in this position and a 0 there. But there's nothing stopping me putting it here if I want as well. So I'm going to do that because that's fun. Row 2 is minus row 2. 1, 1, 0, 0. So they're my columns of the identity matrix. And so this one's a free variable. So let y be equal to t. Then x plus y is 0. So x is equal to minus y. And so x will be minus t. And what have we got? We've got minus 2y plus z is 0. So z will be equal to 2y, which is 2t. So I'm really imagining these two, moving them over the other side of the equation. And so I've got, if I can squeeze it in here, x, y, z is minus t, 2t, which is t lots of minus 1, 1, 2. And so therefore the kernel, oh crap, I keep calling it Ker instead of K. Sorry guys, there's two notations in use. Pick whichever one you think is best, or whichever one's actually in the notes. Which is the span of minus 1, 1, 2. Right. Yes?
What do you do with the columns? Or do you like swap the columns?
Sorry, what's that?
Do you swap the columns? Or like, were you
Here? Yeah, I just put my pivot column in a different spot than I normally do.
Oh, okay, you can do that.
Yes. Well, in fact, you did do that when you're doing Maths 1A and you were doing optimization with slack variables. You put your pivot columns wherever you wanted when you did optimization. So because you've done it once, you must be allowed to do it always. Yeah. So you are allowed to, as long as you have a full identity matrix, you can put it wherever you want, which is really fun, I think, and it does cut down your working ever so slightly. But I could have still done it the other way. I could have put my pivot here if I wanted and put 0, 1, 0 and 0, 1, and it would have been fine. It would have given me a different basis, but the same kernel. Yeah. And the people reading your exam are clever enough to be able to tell. We hope. I'm sure they are. Okay. So that's the kernel. So I really should just warn the people reading this that there are going to be two ways. Way one. Okay. Okay, so let's find the range. Okay, so the range of f is everything that comes out. So it's a set of all of these things, right? It's a set of, I can write it this way, it's a set of all f of x, y, z's, such that x, y, z is in R3. So that's an alternative way of writing it, which I probably should have put back on the other page. How did I write it on the other page? Oh crap, sorry. The alternative way is, I can't fit that in. Can I squeeze that in there? No. That's sad. All right, well, we have an alternative way here. It matches with the way I did the column space here. Okay. So that means I need to find all of these things. So we're going to have a look at f of x, y, z. And it's x plus y, 2y minus z. And I know that if I cover all the possible x, y's and z's, this covers the entire range. And so I want to rewrite this as a span because then I'll know what the range really is. And it's a subspace, so I know that I could write it as a span and that would be a useful way of doing it. So I'm thinking I could separate this out as to something with the x's and something with the y's and something with the z's, like that. So this one's a bit harder to see. I notice that I have three vectors in R2, so I probably can cover as much of R2 as I want as long as some of those vectors are independent. So I notice that 1, 0 and 0 minus 1 are linearly independent, and there's two of them, and I'm in R2, so there must be a basis for the whole of R2. So notice basis for R2. So therefore the range of f is the entire of R2. Yay! I mean, it's currently, at this stage, the span of these three vectors. Yep.
Oh, is that the column space?
Well, it's the range of the linear transformation, but you're right, it is the column space of the matrix.
So if you write the column space, would that be correct?
You're just not allowed to call it a column space if you've been asked for a range. Because they are the same thing, but they have different names. Mathematicians are nothing if not people that give multiple names to the same thing. Sometimes the same name to different things. Okay, let's do our second way, which will hopefully answer your question. So way number 2 is to go via the matrix. So way number 2 is to go back to my original f of x, y, z, and rewrite it as a matrix. So I'm going to rewrite f of x, y, z as matrix times x, y, z. And so let's have a look. I have 1x and 1y and no z's, and this multiplied by this produces this first entry, and this multiplied by this produces this entry. And you'll notice, and it's not a coincidence, that this is the same matrix I drew before when I was finding the kernel. So now I have a matrix, which I shall call A. And I can say, right, the kernel of F is the null space of the matrix A, and the range of F is the column space of the matrix A. And so now, to find the kernel and the range, all I need to do is find the null space and the column space, which is sort of what you're saying. So, to find the null space and the column space, the easiest way is to reduce row echelon form the matrix. And so, I'm going to find the reduced row echelon form of A, for which I'm going to need to go to a new page. Okay. So 1, 1, 0, 0, 2, minus 1. And I really will do the proper reduced row echelon form this time. I'm going to put a 1 in this position, like that, by dividing row 2 by 2. And I'm going to do row 1 minus row 2. Just let me check that. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus a half is plus a half, yep. And now this is in reduced row echelon form because I have as much of an identity matrix as I can possibly fit. And I have a free variable there, which is useful. So from this reduced row echelon form, I can figure out what the column space and the null space are. If I wanted, I could find the row space, but I don't care for this question because the row space doesn't live in linear transformation land. I can now find both of these. So let's see. The null space of A. So first I'm going to let Z be equal to T, then X is equal to minus a half of T, Y is equal to a half of T, and so X, Y, Z equals minus a half of T, T, which is that. And so therefore the null space of A is the span of minus a half, 1. Crap, just making it worse, David. And that's the same as the kernel of the linear transformation. The important thing if you're ever answering a question about kernels and you use the null space to do it is to assert to the person reading it that you know that it really is also the kernel. You'd have to say the kernel is at some point. Okay, so that's the kernel from the linear transform from the matrix. I need to solve for when this is equal to 0, which is what I'm doing here. In fact, I should say find null A. But I can also find the column space of A. Now, according to our normal procedure, the column space of A is the span of the 3 columns and it's already a span, so it's nearly a basis. I just have to find the ones that are linearly independent. And when I get down to here, the ones with pivots are the original ones that are linearly independent. So down here it was, they're the pivots there, so up here it was 1, 0, and 0, 1, 1, 0, and 1, 2. And so I've got that column space of A is the span of 1, 0, and 1, 2. According to the procedure I've learned, but I know that those two are linearly, I mean, they're obviously linearly independent. There's two of them, so they must span the whole of R2. So that is R2, which is the range of the linear transformation. Did someone want to say something? No? I thought I heard a I'm about to ask a question noise. Okay. So that's linear transformations, kernels, and ranges. So just a couple of notes. If your kernel or range does turn out to be the whole of R or whatever, you should always say. So this one I could leave it like this, and it totally is the span of 1, 0, and 1, 2. But those are two vectors in R2, and so they must span the whole of R2. So if it is the whole of R2, you should always say. And in fact, it's a clue when a math lecturer says, what is the range? Instead of saying, what is a basis for the range? It's a clue that it's going to be the whole of R whatever. Because to say what is telling you that it ought to have a name. But to say what's its basis is telling you that, well, it doesn't have a name, you're just going to have to tell me what the basis is. It's not necessarily going to always be true, but it's worth thinking about when you look at past exams and seeing the line-up between answers and questions. That's just more a sociology thing. That's how do maths lecturers write exams, which is a useful thing to be able to know. Okay, I might as well just finish this off. Therefore, the kernel of F is the span of minus a half, 1, and the range of F is R2. If I was writing an exam, I would finish it off so that the person reading it didn't have to look for the answer. So happy markers are generous markers. And happy markers are markers that don't have to do as much work. Okay. So someone mentioned composition. What did you mean by that? Okay.
So I just want...
Have you got it?
Then if I missed something when I was writing the directions.
There are no stupid questions, and understanding what's in the lecture notes is a great thing to start with. First, I will, while you're looking for it, I will at least say what composition is. Composition's a fancy word. When you did composition back in Maths 1A or M, composition is when you put one function inside another. So with ordinary functions, you might do something like f of x is x squared, g of x is x plus 1. And so you'd go f of g of x is putting g of x inside of f of x. Ta-da, that's composition. That's with ordinary functions. So with linear transformations, it's the same deal. With linear transformations, you might have f of x, which is a vector, being 1, 0, 2, 2 times xy. And you might have g of xy being 2 0 minus 1 7 1/2 5 of xy. And so you would do f of g would be, let's doing it the long way. Back here, this was called f of g of x. Right. So f of g of the vector xy would be f of g of xy. Oh, I can't do f of g, and we'll explain why in a second. G of f of xy is g of f of xy, and f of xy was 1 0 2 2 xy, and g of anything was 2 0 minus 1 7 1/2 5 times this thing. And so now we have g of f is this formula. Is whatever this matrix multiplication works out to be. Let's see. 2 times 1 plus 7 times, so that's 2 plus 14, which is 16. 0, so it's 14. 0, that's 2 times 1. 0, 1. Minus 1 plus 10 is 9. Ta-da! I composed them. And so now I don't have to first figure out what f of xy is and then sub it into G. I can just do this matrix and it'll do it all in one go. Have you found it?
Yeah, but that will solve it.
Good. That solves the problem. I mean, you can literally do it this way, and that's just fit it all on one screen, especially if I zoom out a little bit.
So essentially, like positions like the multiplication of the matrix.
Yeah, and so you're right. When you compose these, it turns out to be the same as multiplying the matrices. The point is that you may not already have matrices when you start. So linear transformations, they all have a matrix, but you might not have it to begin with. And so the quickest way to do the composition of linear transformations is to first find their matrices, and then off you go. And the reason this works is, well, I mean, look at it. But also, this has to be the standard matrix for this linear transformation, this new one, because a linear transformation only has one matrix. And so if I find it, it must be the matrix. So if I now wanted to find the kernel and range of this linear transformation, I'd just do the kernel and range of this matrix. The reason I couldn't do it the other way around is because I would have had to try and multiply these matrices the other way around, and it's not possible to multiply those matrices the other way around. Right. Because this, if I did the other way around, I'd have to have a row with 2 lining up with a column with 3, and they wouldn't work. So some thoughts, yes?
So if we do know the kernel range of the G matrix and the F matrix, is there a way to make the overall composition? Or is it just better just to like do it from straight line?
So I'm just going to restate that so that people can hear it on the video. So you're saying, and let me see if I've got this right, if you do know the kernel and range of F and the kernel and range of G, can you figure out the kernel and range of G of F? And the answer is, most of the time I don't think you can. I could be wrong about that. Ooh, I think you can. Okay, we'll try one, okay? You have to at least know what F does to things, if F is the one on the outside. Or G, you have to know what the outside one does. Yeah, I reckon we can figure this out. Okay, we're going to do an example where you only know one of them. Okay? Sweet! How exciting. Okay, I'll just try and make up an example that works. Give me a minute. So G is going to send R3 to R2 so that, no, not so that, and G has, the kernel of G is going to be the span of 1, 0, 0. I don't think it's going to work. Okay, I think give me a minute. I don't like it. I think what's going to happen is that if you can tell what the range does as long as you know what the second function does. If you know the range of the first function and the formula for the second function, then you can figure out the new range. And if you know the kernel of the second function and the formula for the first one, you can figure out the kernel for the composition. Because of the kernel living in the start space and the range living in the end space. All right, here we go. So G sends R3 to R2 with the range of G being the span of 1, 0, say. Okay. And F sends R2 to R, let's be creative, R4 with F of x, y being x, y, x, y. That looks like fun. Okay. Find the range of f of g. Okay, this is fun. I like making up new kinds of questions. So I'm just going to draw a picture of what's happening here, and I'll do it on the next page. I'll try and keep that all on the page at the same time. Okay. So G sends R3 to R2. That's what G does. And F sends R2 to R4. Okay, that's what we have at the moment. And f of g puts g inside f. So the one that goes direct is f of g. Now it looks backwards, but you've got to remember that the one that's here is the one that's closest to the x, so it got done first. G was done first and then f. In terms of the matrices, it will work out the matrices in the correct order. But yeah, that's just a quirk of the way that we write functions. Because with the matrices, whichever one is closest to the x is the one that happens first, and that's the second one. So, yeah. Okay. So this is what's happening. And we also know what the span of G, what the range of G is. Okay, that's an R. So all of this ends up here. I've drawn it as a line because the span of 1, 0 is totally the x-axis. I might just make it a little bit bigger so it's a little easier to see what's going on there. Okay, so if I do f now, the things that came here ended up here. So to figure out where the range of the whole function is, I only really need to know what happens to these ones. Because to do the range of f of g, I have to know, when I start with these ones, where do they end up? And all of these ones end up here. And then to track where they go, I only need to know where these go. Okay. Okay, so the range of f of g is all of these things. So it's f of g of x, such that x is in R3. So let's see, f of g of x, damn it, too many brackets, is the same as f of g of x. And if you're g of x, you must be something in the span of 1, 0. So that would be f of something times 1, 0. Yes! And linear transformations allow me to do this, because I can bring constants out the front of linear transformations. That's one of the properties of linear transformation. And f of 1, 0, well, according to the formula for f of 1, 0 will be 1, 0, 1, 0, according to this formula here. Okay, therefore, the range of f of g is the span of 1, 0, 1, 0. I'm so excited that that actually worked. It's so cool. Yes? I don't know. I don't see why not. You can totally do this with the information you have in your course. Not that I didn't write the exam. I haven't seen the exam. I usually don't see the Maths 1B exam until the following semester when someone's got a past exam and they're going, hey, this is a past exam and what's in it. But it's totally a possible thing. Like, you have all the information in your course that you need to solve this problem. So let's just track through to see how I did that. This was the information we started with, and I thought, okay, I started to think about what this means here, and then I thought about what the definition of the range was, and so I figured out what f of g of x was, and I got this. I should probably put some, oh, that's probably not a, I should probably put a note in here, since g of x is in the span of 1, 0. Yeah. Okay. I mean, those of you who are not in the revision seminar and have not watched it, those people who I can't talk to because they're not watching the video, those people probably would freak out a bit. But it is technically possible to do it. And I didn't know how to solve this problem yet either. I just had an instinct, because I've done Maths Learning Centre for 10 years. I had an instinct for how it might go down, but I wasn't sure. So until I actually tried this and wrote this bit down, that's when I got really excited, because I could see what was going to happen at that point. So it wasn't until I put this together in this format and subbed in something in the span of 1, 0 into this position was I able to figure it out. Yeah. Cool. Now let's do some what ifs. What if it had been the span of two things? Well, over at this stage here, it would have been, K1 of something and K2 of something. And I could still have expanded it out, because linear transformations allow me to do that. And so I would just end up with a span of two things. And that's really cool. But kernels, I don't think would have worked the same way, because with a kernel, you need to know what comes out to be equal to 0. And so, actually, yes, okay, let's talk about that too. I'm just thinking about kernels, because I'm thinking everything in the kernel ends up at 0 here, and so it'll still be 0 after. So if I do a composition, then everything that was in the kernel before is still going to be in the kernel afterwards. But I have a feeling I might pick up extra bits in the kernel that weren't there before. So I'm just going to think about kernels for a second. Let's see if I can do an example. I'll try again. F sims. Oh. This is going to be harder. Just a second. Oh, and that's not in R3. That. It's going to take me a while to figure this out. Just a second. X, Y, Z. R3, R2. G. So yes, okay. Yeah, I think I've got it. All right, let's find the kernel of G of f. Okay, so I'm going to draw my picture. I was in R3, and then I ended up in R3 again afterwards. It should be the same size, but sorry about that. And then I end up in R2 after that. And then the kernel of f, you notice I keep switching which one's first just to keep you on your toes. So the kernel of f ends up at 0 here. And then the kernel of G ends up at 0. Damn it, that's a bad colour. It's bad on my paper, it's fine on your screen. Okay, cool. Kernel of G might be, you know, has to contain 0, obviously, because 0 goes to 0 all the time. Ends up there. So the thing is, it might be, you see all of this ends up at 0. I actually need to figure out which part of this ends up in there, because anything that might be a little bit bigger, because these green bits might end up inside there, and then end up at 0 again at the other end. So any vector in maybe here might end up in that orange bit and end up at 0 after all. So the kernel of f is totally contained in the kernel of G of f, but there might be a bit extra. Okay. Okay, so this is the kernel of f in blue, and this is the kernel G of f in green. All right, let's see. Right, so span. So how are we going to do this? Well, let's just see. The kernel of G of f is the set of things such that G of f of x is 0. That's what we're going to do. So if G of f of x is 0, that means G of f of x is 0, which means that f of x is in the kernel of just G, because that's what it means. F of x being 0, you know, G of thing equals 0 means that the thing is in the kernel. That's a definition of the kernel, which means that f of x is in the span of 0, 1, 0, 1, 0, 1, which means that f of x is totally something like, you know, the span of those things. So it's going to be like a of 1, 0, 0, 1, 0 plus b of 1, 0, 1 for some a and b in R, because that's what it means to be in a span. I have no idea where this is going. I have an instinct, but I'm not sure. So I'm just going to turn it into a single vector. So it's b, 0, b, and then 0, a, 0. So when I add them together, I get this. So that means that I need f of x, which is 2, 0, z, to be equal to this. That's what I need. Because that's what f of x is, right? F of x is 2y plus x, 0, z, because that's what it said back here. Okay, so the a has to be 0 for that to work. So 2y plus x has to be b, 0 has to be a, and z has to be b. So 2y plus x has to be z. That's what that says, because they're both equal to b. So that's the kernel of the whole thing. We've just discovered that if f of g of x comes out to 0, then 2y plus x has to be z. Yay! So the kernel of f of g, oh no, it was g of f, sorry, is the set of x, y, z's such that 2y plus x is equal to z. Good enough for me. If I wanted a basis for that, now I would find a basis for this and see what happened, and find all the vectors that satisfy that single equation. I feel like this one would be a bit mean in an exam. Or possibly they could do this to you, but maybe put a part A to give you a little bit of it and then a part B to give you another bit and step you through it. But I'm extremely excited that I was actually able to come up with such a thing. Yeah. Cool. But I think the main moral for me is to realize that the kernel of g of f is allowed to be a bit bigger than the kernel of f. They might actually be the same, but it's usually got a few more vectors in it. That seems reasonable that it could happen. Yes?
Can we go over continuity of two variables?
So switching over to something else entirely? Is that what you're saying?
Yeah.
Okay, cool. I might have a look at our other lists that we've got and talk about some of them first, but we'll see what we can get to. There's quite a few things on the list, but we'll see how we go. I think I might stop there. The only other thing I would say about kernels and ranges is that there's a theorem that says how many dimensions kernels and ranges ought to have. And therefore you can be given questions where they tell you nothing about any of the formulas, and they just tell you, well, the dimension of this, the kernel of this is 2, and the range of this is dimension 3, and you can figure out whether it's possible or not by matching them up. So I knew for a start that just this information here was enough to tell me that the kernel of G had to have at least a dimension of at least 1, because there's not enough room to fit the whole of R3 in here, so some of it must be left behind in the kernel, which is how I think about it. These ones all end up at 0, so they get squished away. So it ended up having dimension 2, but that's fine. So there's things like that where I can know that, and also I can know that if the kernel of G has dimension 2, then the range of G will have to have dimension 1, because together the 2 and the kernel and the range's dimensions add up to wherever you started. Yeah. Right. So even if I couldn't actually tell you what the range actually is, I could tell you that it has dimension 1. Sweet. Okay. That's enough of that. So there's this one example that was, I've been asked at least twice in the Maths Learning Centre and once via email to do today, and I thought I would do it now. It's sort of separate to everything else, but I wanted to cover it so that I could direct people to the video in the future. So this is like a power series, Taylor series example. And it goes like this. Use a power series to estimate the integral from 0 to 1 of e to the minus x squared dx to within 0.001. It's one of the practice questions in the list of practice questions. I think it's 78 in the calculus one, I think. I didn't write it down, I'm sorry. And I just thought it would be useful to talk about it because it will contain a lot of information that's really useful stuff. As usual, feel free to interrupt me at any point and ask questions. Yeah. So, upstairs, mate. If you're going to the toilet, that's where it is. So, when I look at this, I'm going to tell you how I think about the whole thing and see if you can follow my problem-solving process. When I look at this, I think, okay, power series, it seems reasonable. What I should do is figure out a power series for e to the minus x squared. I know I can't integrate it directly anyway, because e to the minus x squared doesn't have a formula for its integral. That's impossible to write a formula for that, which is very sad for statisticians and physicists the world over. But there's nothing we can do about that. And so we will write a power series for maybe e to the x, and then sub in the minus x squared. That's what I'm thinking. That's my guess. So e to the x I know for sure is the sum from n equals 0 to infinity of x to the power of n over n factorial. I definitely know that, where we say that 0 to the 0 is 1 for calculating this. Okay, so just the long version of that would be 1 plus x squared on 2 plus x cubed on 6 plus x to the 4 on 24 and so on. Okay, so e to the minus x squared should be 0 to infinity minus x squared to the n over n factorial, because I've just subbed in minus x squared into this. And I know that's fine because e to the x's power series converges no matter what x is. So I should probably say that. Converges for any x. And you're allowed to just say that. It's one of the ones that you're supposed to just know, that e to the x's power series converges no matter what x is. So e to the minus x is totally going to, x squared is totally going to be equal to that. And so I suppose I could expand that out. I'm going to have to integrate it. So it might be easier to integrate if I did this. So minus 1 to the n x to the 2n. So I've just done the n power on both the negative and the x. And x to the 2 to the n is x to the 2n. Okay, that's good. So if I want to integrate that from 0 to 1, I think the theory of power series says that I can integrate from each term separately from 0 to 1. So if it was just a finite sum, I could totally just do each integral separately, because that's fine. And the infinite ones bothers me a little bit, but I'm pretty sure the theory of power series says that I can do them all. So the integral from 0 to 1 of e to the minus x squared dx should be this. Okay. Okay, so the minus 1 to the power of n is a number, and so that won't change. And this is a number multiplied on, and so that won't change. And the power will go up by 1, and I'll divide by the new power. Sweet. I just want to check if this works when n is equal to 0, because that's often a case that it's a bit dodgy and weird. So if n is equal to 0, we actually just have minus 1 to the 0, which is 1, x to the 0, which is 1, and 0 factorial, which is 1. So we just get 1. And when you integrate 1 from 0 to 1, when you integrate 1, the integral should be just x. So let's say minus 1 to the 0, 0 factorial, 2 times 0 plus 1 is 1. X to the power of 1 is x. Okay, it's working when x is 0. Cool. So that should be n equals 0 to infinity. Right, so when x is 1, we get minus 1 to the n, 1 to the 2n plus 1 over n factorial 2n plus 1. And when x is 0, we get minus 1 to the n over n factorial 2n plus 1. And 0 to the 2n plus 1 is 0, no matter what n is. Cool. The only one that would be a little bit difficult to figure out is that if we ended up with a 0 to the power of 0, which doesn't usually have an answer, but in the context of power series, 0 to the power of 0 is 1. But I don't need to worry about that because it's 0 to the power of at least 1. So that's cool. That sounds like it's actually inside the roof, doesn't it? I wonder if we have a possum. I lived in the Schultz building once, and we had a possum die in the roof once. And yeah, it was about a week before they could find the dead body and remove it. It's pretty awful. Minus 1 to the n over n factorial 2n plus 1, because 1 to the power of 2n plus 1 is 1. Okay, cool. And that's the answer. And the question is, if we want to integrate, if we want to get that accurate to within 0.001, I'm going to have to figure out how many of them to do. Quickest way, I reckon, is to just keep adding them on until it doesn't change by very much. Yep?
Oh, do we minus 1 at the end? Because you said 0 to the power of 0.
But I'm not going to do 0 to the power of 0 because when n is 0, I end up with 0 to the power of 1. So it'll all be okay. No? Yeah. Yeah, so just be careful, you might have to minus 1 as well. If this started at 2n, then we'd have a problem. But because it's 2n plus 1, it's okay. Okay. So, well, it seems to me that we're just going to do as many of them as we can and see when it gets to within the right zone. So 1 over 0 factorial, I'm just going to do it. So 0 factorial is 1 times 1 minus 1 over 1 factorial is 1 and 2 times is 3 plus 1 over, now we've got 2 factorial is 2 and 2 times 2 times 1 is 5 minus 1 over 3 factorial is 6 and 3 is 7. Okay, so there's our pattern. It looks like we're going to have that. And we need to keep going until this is less than 0.001 because that's how much it changes by. All right. I don't know how many we're going to have to do. This is when we break out a calculator and keep going until it doesn't change by very much. Okay. Minus 1 divided by 1 times 3 plus 1 divided by 2 times 5 minus 1 divided by 6 times 7 plus 1 divided by 24 times 9. Well, that didn't change by much last time, did it? I really should be writing them down as I go. So we're up to 7474.001, wasn't it? 001. Okay, so we want this last one to not change. So minus 1 divided by 120 times 11. That changed by 0.001, didn't it? Yes, it did. Okay, so one more. There we go. We didn't change that last coordinate decimal place. I'll do one more just a second. I just want to be sure. Yep, okay, cool. So we're saying 0.747 within 0.001. Yay! I just kept adding it on until it didn't change by more than 0.001. And then I was sure. If they had asked me how many terms do I need in order to get it to within 0.001, I could have just done it. But if I want to say, well, how many terms to get within 0.00001, then now that I know how much it changes by each time, that means that I can actually say that I only need to figure out which term I'm up to. So I could have said that, well, which n makes this less than 0.001, and that would tell me which n it is. And there's actually like an alternating series thing, I believe, that the error in an alternating series is less than or equal to the term you're up to. So that's how I would do it. I don't know if that's how you're supposed to do it, but I have used the main things, which is I know a power series for e to the x, which means I can find a power series for e to the x squared, and I know I can integrate each term separately because that's part of the theory of power series. Right. Before I move on from power series-y stuff, does anyone have any specific questions about them that you would like to ask? Yep.
So the question I asked used the power series. You kind of started with the power series, but then made it into an alternating power series.
Uh-huh.
I suppose that doesn't really affect it, though, when it says it's still a power series, isn't it?
Yep.
It's an alternating.
Even if it's alternating, it's still a power series. The power series is to do with the fact that there's an x to the power of something. It doesn't really matter what else there is, and it's still a power series. Cool. But yes, it's sometimes a bit difficult to tell when they say use something, because I use it as my jumping off point and then did other stuff, and that's okay. As long as at some point in my working I used a power series, I should be all right. I mean, this is one of the keys to actually why power series are useful. I can do things like integrals of this to any accuracy I want by using power series. I don't know how a calculator actually does it. It probably has something fancier than this, but maybe it doesn't. Maybe it's still just a power series. Cool. I believe that's the first question in that block in the practice questions, which is quite intimidating. But my first instinct to this one was just to start with this because that's something that I know. You're supposed to be able to just remember this. It's one of the things they want you to be able to remember. Yeah. Okay, cool. Hey, this is another one of those things. In the linear transformations, I said each linear transformation has exactly one matrix, and so if I think of a matrix that works, then it must be the matrix. Same deal here. A function only has one Maclaurin series, so if I think of a series that works, it must be the Maclaurin series. And that's a really interesting way of someone saying, you know, find the Maclaurin series for e to the minus x squared. And you go, all right, well, I can just do this. I don't have to actually do the derivatives unless someone tells me to use derivatives to do it. I'm allowed to make it out of other Maclaurin series if I want, which is really cool, at least to me anyway. I like that argument though. My entire honours project was finding the equations of lines by going, well, there's only one line through these 2 points, and here is an equation that works, therefore it's the equation. Yay! I like finding bases for subspaces in the same way. It has to have two, here are two, works. So, yeah. Cool. All right. The other thing that several people have asked me about was doing eigenvalues of linear transformation, of matrices, without actually knowing what the matrix is and just having a picture. So I just wanted to talk about that. This is going to be hard for me to do off the top of my head. But eigenvalues from a picture. So when you first learn eigenvalues, they're a property of a matrix. But because matrices define linear transformations, eigenvalues are therefore also a property of a linear transformation. And so thinking of a transformation in the literal sense of transforming space, I can now think of eigenvalues by thinking of what they do to vectors. And so this is where it comes from. So matrix, A times X is a linear transformation. And so I would expect that things to do with the matrix would have things to do with how the transformation works. And we've already seen that. Things to do with how, what things come out of A times X, like what the columns produce is things of what comes out of the matrix. And what makes the matrix equal to 0 is what makes the linear transformation equal to 0. So we've already seen that. And this is one of the more geometrical things. So to do this, I need to think about the way think about functions in terms of that picture I drew with the before and after picture. And when I have vectors here, I can multiply them by the matrix and figure out where they end up afterwards. So it may be, for example, that my matrix turns this into this, and maybe it will turn this into, well, maybe it will stay, that one will stay the same. And it will always turn the origin into the origin, and I could pick any vector here and see what it looks like afterwards. So you can think about that this way. Okay? So I can think about my matrix as being a linear transformation and look at a collection of dots which are vectors before and figure out what all of their values are after I do the transformation and draw them afterwards. And so that's the before and after sort of picture of linear transformations, or indeed of any functions. And it's one of the more useful ways of doing multivariable calculus if you ever have to do that further than Maths 1B. And so I can try and see, based on a picture, which vectors are eigenvectors, because an eigenvector has the useful property that it's on the same line it used to be through the origin. So an eigenvector does this. A times the vector is some multiple of the original vector. And so, for example, it might be something like, let me see if I can find the eigenvector of this one. I might not be able to do that. Oh, I found them already, but anyway. So it may be that I have something like this, and then afterwards it's there instead. Damn it, I did not do a good job of that. So the idea is that it was here, and now it's still on the same line it was before. That's an eigenvector. And what happened is I multiplied its length by lambda. So this was v before, and now this is lambda v. And that's what an eigenvector is. And it can look a little different to that. Sometimes, if my lambda is negative, it will switch my eigenvalue to the other eigenvector to the other side. Let me do it in nice orange. So this one could end up over here, like that. That's an eigenvector as well. This is lambda is negative, lambda is positive. And the only other thing that might happen is that your lambda might in fact be 0. And so it is technically possible that if you have a vector somewhere, then it might end up afterwards like that. there's sort of three possible pictures of an eigenvector and what the matrix does to it. And you can also think of what happens if the lambda is more or less than 1. If the lambda is more than 1, then the vector gets further out. If the lambda is less than 1, then the vector gets further in, because it makes it shorter multiplying by a number less than 1. And that's how to think about this. Which means that if I see a picture, pardon me, which shows clearly where vectors go, I might be able to be lucky enough to find an eigenvector. For example, in this picture, this blue dot is an eigenvector because it didn't move at all. There's V, there's the result of V, and so we have AV is V. So the lambda is 1 because it stayed in the same position. Whereas this one isn't an eigenvector because it moved into a different direction. It was on the x-axis before and now it's on the line y equals x, so it's not an eigenvector. Okay. So we can now, knowing this information, make up some questions. I'm going to do mine in 4 different colours, just so it's easier to see what happens. And maybe I'll do this off screen so that we can reveal the answer afterwards. Just take me a little while to figure out what I want to do with this. It's going to be there. It's going to be there. This one. This is hard. I imagine that the person who came up with this that assignment question was extremely proud of themselves. I may only do one example of this, possibly two. All right. There we go. So I'm going to work my way around and see what happens to all the points that I know about. So this point, I'm going to assume that these are ones here. So this point 1, 1 is still at the point 1, 1 afterwards. So I have A of the vector 1, 1 is still 1, 1. So it's an eigenvector because, well, the eigenvalue is 1. And this one down here is as well. Okay, cool. And 1 and minus 1 plus 1 ended up over here at plus a half minus a half. Which is on the same line through the origin, so it's an eigenvector, and it would be minus a half times what it was before. And this one here ended up on the other side too. So a of 1 minus 1 ended up over here at a half, minus a half plus a half, which is minus a half of what it was before. Now this is all working the way I should. If the plus version is an eigenvector, then the minus version has to be an eigenvector as well. In fact, anything on this line has to be an eigenvector, and that's working out the way it is. So it's a 2 by 2 matrix because it goes from R2 to R2, and so therefore it can only have 2 eigenvalues, which means I've found them all. 2 by 2 has 2 eigenvalues. And so we have lambda is 1 and minus a half. In fact, I can even figure out what the matrix is from the information I have now. Because I know what A does to a couple of vectors that are independent, I should be able to now figure out the matrix is. Yes?
Is the bottom one true? Yeah, that one true. The half the end. Yeah.
Yeah, cool. Good noticing. I am nothing if not prone to minus sign errors. So, cool. I should be able to figure out what this matrix is if I wanted, because I know what A of 1, 1 is, and I know what A of minus 1, 1 is. So if I added these two together, that would give me A of 0, 2, and I could divide that by 2, and that would give me A of 0, 1, which would be the second column of the matrix. So I might even actually do that. You know, didn't ask to do that, but... So A of 1, 1 is 1, 1. A of minus 1, 1 is a half minus a half. So therefore A of 0, 2, by adding these two, is 1 plus a half is 3 on 2 is that. And so therefore A of 0, 1 is 3 quarters, 1 quarter. And when you multiply a matrix by 0, 1, it tells you what the second column is. And actually, let's look at this. A of 1, 0 would be this minus that. So 1, 1 minus 3 quarters, 1 quarter is, oh cool, 1 quarter, 3 quarters. And so therefore, A is 1 quarter, 3 quarters, 3 quarters, 1 quarter. Ah, there you go. Actually, I would have expected it, I should have expected it to be a symmetric matrix because its eigenvectors were orthogonal to each other. And a symmetric matrix's eigenvectors are orthogonal to each other. And in fact, a matrix whose eigenvectors are orthogonal to each other is a symmetric matrix. That's cool. So this is a little bit of the sort of thing that you go on when they tell you what the linear transformation does to some vectors and you have to figure out what the standard matrix is. It's exactly this working. Cool. So the only other thing that might happen is that your picture here might turn into not a box anymore. So I just want to do that one as well. I mean, technically they could do this in 3D, but the diagrams would be extremely hard to read. Yes?
I know it's kind of the same thing, but isn't it the first and second rows, not the first and second columns?
No, it is totally the first and second column.
Okay.
Because we multiply by a column, and therefore it tells me what the columns are. Just checking this. If I multiply this by 0, 1, it gives me 0 of this and 1 of 3 quarters. and 0 of this and 1 of 1/4. If you had put the vectors as rows on the other side, it would have told you what the rows were. Be careful if you look at online resources, some people do eigenvectors with row vectors on the left, whereas here in Maths 1B in South Australia we do eigenvectors with columns on the right. So sometimes it turns out the other way. And I wouldn't have mentioned that unless you asked that question, so well done. Okay, so it is technically possible, even though these are the wrong colours, I'm totally thinking in my head of this as like a Wiggles transformation. And I should really have done them in red, yellow, blue and purple, because that would have been fun. Maybe next year. So interestingly, in the very early Wiggles, the blue wiggle was green. So it is technically possible to get something a little more like like that. It's extremely hard to draw where all the colours go. The point of this is that this point here, well, I don't actually know where it is within this line, I can't really tell, but I'm going to assume it's still at the end. And this, all of these end up here, munched into that orange bit. And so I can't actually tell from the information because I don't really know whether these have switched in reverse or something. But I can probably guess that A of 1, 1, I should do them as columns. We have to interpret our coordinates as column vectors for this to work, which may be what you were thinking of. A of 1, 1 has become 0, 1. So this one has moved inwards to be just there. And A of, actually if we look at this one, I'm assuming that that point didn't move. A of 0, 1 is still 0, 1. And we also have A of 1, 0 became 0, 0. So in fact, I actually have enough information already to tell me what the matrix is. This is the second column and this is the first column. So I have eigenvectors here because this one has the lambda equals 1. And this one has the lambda equals 0, which is okay. And this one's not an eigenvector because it's not a multiple of what it was before. So A is in fact equal to 0, 0, 0, 1, and the eigenvalues are lambda equals 0 and 1. Sweet. Yes?
So why a 1, 0, 0, 0?
Because 1, 0 was here,
Okay.
between the orange and the pink, and it's now here between the orange and the pink. This one's probably a bit too hard to expect people to do an exam and get the answer as the one you expected, because there's a lot of different options for what could have happened. Yeah. We don't really know if 1, 0 actually ended up down here at 1, 1. But if it did that, everything else would have had to rotate around, and so I have a feeling the colours wouldn't have matched up properly. So I'm just making an assumption here with this one. All right. This one's going to be so hard to put online because I have to do that all manually. It doesn't do it automatically. And I like to tell people which bit of, what timestamp everything starts at, and there's a whole lot of stuff in it, so it's going to be a bit difficult. So please forgive me if it's not online by tomorrow morning. My parents are coming over tonight, so I won't be able to do it for homework tonight. By 10 o'clock tomorrow it should be ready. Okay, so what did you ask? Okay. It's about limits. Okay, cool. And we've also got some stuff that someone asked about the intermediate value theorem. What did you want to know about that? All about it. All about it? Okay, cool. What time is it? Oh, crap. We're already at the end of our time. I can't do both of those. I can still go for another, like, half an hour or so. I might not be able to do both of those, but I'll do my level best. I'll do the IBT. Sorry, start with the limits? Okay, so that's what you wanted, continuity in multivariable functions? Okay. Okay, cool. Okay, so, right. When you, all right. So, a function is continuous at A, where A in our case is actually a vector, like it's, you know, x, y or something, when the limit as x goes to A of the function of x exists, and the function value exists, and the limit as x goes to A of the function is equal to the actual function value. So that was true with ordinary limits, but I have changed one thing and done them as vectors. Yes? I'm getting there. Okay. So this is a definition of continuity, but you have made an important point in that for this limit to exist, it has to exist from both directions. Or in the case of multivariable functions, from every direction. So I'm just going to add that in. So that's the definition of being continuous, and I know that the limit of x approaches A of f of x only when it exists from every direction. Okay. So the limit as x goes to A of f of x exists only when it exists from every direction. And that's fine with ordinary limits in one variable functions because there's only two directions. You can go from the left or from the right. But in 2 dimensions or 3 dimensions or however many dimensions you want, you know, if you're in 2D and you've got a function of both x and y, there are multiple ways to approach. You could go from the left, from the right, from the north, you know, from the east, from the west, from the north and south, from northwest, spiraling round, along a curve. Like there's infinitely many ways to approach that. And so it can be very difficult to figure out whether a limit exists at all. Okay. So in 2D, 3D, etc., there are so many directions it can be hard to tell if it exists or not. Okay, cool. I just wanted to write it down so that it wasn't lost in just the audio. Whereas in 1 dimension, well, there's only 2 directions, so you can do them both separately. Okay, so as you say, it can be easier to tell that a limit doesn't exist than it is to tell if a limit does exist. So the classic way of telling if a limit doesn't exist is to try a few directions and a couple of them come out as different answers and ta-da, a limit doesn't exist. But how to tell if they do exist and what the limit is if it does exist is the harder bit, and that's what you wanted me to talk about. Cool. It's just going to be easier with examples, but I will just say two things in my head that are useful for figuring out if limits exist. One is to use polar form.
But do you use polar form to prove that the limit exists?
For showing that they exist. Yep. One is to use polar form. That's one strategy. And the other one is to use the squeeze theorem. They are the two strategies I know that allow us to show that limits exist. And that's all I've got that I can think of. Other than just knowing it exists because you look at it and go, well, it's polynomial. It totally exists. You know, it's made of functions that I know work. So, you know, just knowing stuff. So if you don't already know, they're my strategies. So I would do an example, let's see. For y not equal to 0 and 0. Yeah, let's do that. Pretty sure that'll work. This may even have been one of the assignment questions. I can't remember. I'm just making it up. Okay, so this is a classic. So we would like to tell if that limit exists when x is 0. So we're going to go when x and y are 0. So the limit as x and y goes to 0, 0 of f of x. That's what we're going to figure out. Okay. So the first thing I would try, even before I tried anything else, would be to try from a couple of different directions. So let's try along the x-axis, which is y equals 0. So the limit of x, y approaches 0, 0 of f of x should be the limit as x goes to 0 of, well, when y is 0, the answer is 0, so the limit is 0. Because this says that when y is 0, the answer is 0. Okay. Try along the y-axis, which is where x is equal to 0. So we get the limit as x, y approaches 0, 0 of f of x will be the limit as y goes to 0 of 0 times sine 1 over y, which is the limit as y goes to 0 of 0, which is 0. Sweet. Okay, so if the limit exists at all, it's going to have to be equal to 0. So even if you didn't have time to figure it out, you could just make it say, I don't know if the limit exists or not, but if it does, it's 0. Because these two directions have got 0, so the limit has to be 0, whatever it is. Yeah?
Or is it enough to use like y equals mx?
No, it's not enough to use y equals mx. Because that's coming in along a straight line path, and there are some very crazy functions that if you come in along a curved path, give you different answers than if you come in along a straight path. So, okay. All right. So I would try one more when y is equal to x. Try along y equals x. The limit as xy goes to 0, 0 of f of x is the limit as xy goes to 0, 0, no, just a second, x going to 0 of x sine 1 over x. Ah, what is that? I'm going to have to figure out what that limit is in order to tell. I'm hoping the limit is 0, Because if it's not, then it's not going to exist. Well, the only way I know to do that limit, which is now a one variable limit, is to use the squeeze law. Because, you know, it's not like I can turn it into a fraction because the fraction's on the inside of the sign. Oh, wow! It's sine of 1 over x over 1 over x. Ha! Yeah, I could totally do that too. That'd be fun. But, you know, not important. The squeeze law will do this for me. And since I'm going to use the squeeze law anyway, I might as well use the squeeze law on the original function. Nothing up my sleeves. Why don't we use the squeeze on the whole thing? So let's consider x sine 1 over y. Well, we know that sine of anything is between minus 1 and 1. That's always true. And so if I multiply by x, it'll be between minus x and plus x. There are a few problems. If x is negative, then I'll have to switch my inequality signs around the other way. So it's going to be a little easier to do this between, like, the absolute value of this instead. So the absolute value of sine is between 0 and 1. And now if I multiply everything by the absolute value of x, I get that. And the reason I did that is so that I didn't have to switch my inequalities around, because I've multiplied by a positive number. And so I know that the limit as x goes to 0, as x and y go to 0, of 0 is 0. That's this side. And the limit as x and y goes to 0, 0 of mod x is 0. That's this side. And therefore the limit as x and y goes to 0, 0 of x sine 1 over y is also 0 by the squeeze law. Well, this anyway. And if the absolute value goes to 0, therefore the actual function goes to 0. Yay! So therefore the limit as x, y goes to 0, 0 of f of x is indeed 0. So the idea being that if your function is such that your function is always between two things and those two things go to 0, then your function has to go to 0, works perfectly well in multivariable. So that's my first thing. Yes? Yep. That's my first example. My second example would be something that uses polar form. Okay. Yep. You could use polar on the previous question, probably. I could try it. Let's just try it with polar. Or let's try this. So for r greater than 0 and theta from 0 to 2 pi. Sweet. So let's see. X, f of x is x sine 1 over y, which is r cos theta sine 1 over r sine theta. And because I've got crazy thing inside sine, I probably have to use the squeeze law anyway. Yeah. Because the r is trapped inside the sine here, there's nothing I can really do. The only way I'm going to have to deal with that is to use the squeeze law anyway. So just the fact that this r goes to 0 isn't enough. I need to make sure that this thing is less than or equal to something. Yeah. So I would probably do exactly what I did before and actually say something like the absolute value of cos theta is between 0 and 1. The absolute value of sine of 1 over r sine theta is between 0 and 1. So therefore the absolute value of is between 0 and 1, and therefore 0 is less than r, just multiplying everything by r is less than or equal to r, and r is positive, so I don't have to worry about any of that stuff, and that's why the r ended up being able to be on the inside of the in absolute value. And so the limit as r goes to 0 of 0 is 0, and the limit as r goes to 0 of r is 0, and therefore the limit as r goes to 0 of cos theta sine 1 over r sine theta is 0, and therefore the limit as r goes to 0 of f of x is 0. Yeah. That's what I would do if I did polar form there. It was ever so slightly simpler in the end. Technically, if you do polar form, you're supposed to use the squeeze law if you get causes and sines, like in complete technicality. All right, let me do the other example I was planning to do. So this one, I would still try multiple different directions. This one I would still try multiple different directions. So try the x-axis, where y is equal to 0. The limit as x goes to 0 of f of x is the limit as x goes to 0 of 0 over x squared plus 0, which is the limit as x goes to 0 of 0, which is 0. Okay, so if the limit exists at all, it has to be 0. Well, I think we're doing pretty well. I'm going to believe it works. If I go along the y-axis, the same thing will happen. Did you want this? If I go along the y-axis, the same thing will happen because it's symmetric in the x and y. 0, we end up with the limit of f of x is 0. If I try x equals y, yeah, it'll still work. Harder to tell, though. Actually, no, it won't. Try x equals y. So let's see, the limit as x goes to 0 of f of x is the limit as x goes to 0 of x times x over x squared plus x squared, which is the limit as x goes to 0 of x squared on 2x squared, which is the limit as x goes to 0 of a half, which is a half, which isn't 0. So therefore, the limit as x goes to 0 of f of x doesn't exist. There we go. I was going to use polar, but I didn't have to. That's why you should always do 3. I always do those 3. And then if they start to work, then I'll go, oh, well, I'm going to try polar. Okay. So, let me try polar on that and see what happened, okay? X is r cos theta, y is r sine theta, x squared plus y squared is r squared. And so therefore f of x, which was xy, x squared plus y squared, is now r cos theta, r sine theta over r squared, which is cos theta sine theta. So if it exists, the limit as x approaches 0 of f of x should be the limit as r approaches 0 of cos theta sine theta, which is different for different thetas, and therefore the limit doesn't exist. So I could have gone direct to polar, but I actually find this a little easier to do. Okay, so here's a question. What should I change this to so that the limit will exist? There's lots of things I could do. Anyone got thoughts?
In the denominator, if you change it to x squared minus y squared?
Oh, yeah? We could give it a try. No idea what that's going to do. What was your reasoning? Was it just a trying something out, or was it a...
Yeah, I kind of went through quickly and thought it was 0, but started to doubt it now.
So x squared minus y squared doesn't even exist when x is equal to y, so we would have to redefine our function to be maybe 0 when x is equal to y. And we wouldn't be allowed to use the line y equals x anymore. But you're going like, you've got like r squared cos squared minus r squared sine squared, which would be cos 2 theta with an r squared. Actually, I think if we tried that, let's do some what ifs. What if it was xy over x squared minus y squared? Then that would have become r cos theta, r sine theta, r squared cos theta squared minus r squared sine theta squared. And I notice an r squared here and here and an r squared on the top because of the r times the r. So I can divide the top and the bottom by r squared. And it still doesn't involve r. And so it will be different answers for different thetas still. Interestingly, this is a half of tan 2 theta, if you're wondering. Because the top is a half of sine 2 theta because of trig identity, and the bottom is cos 2 theta, and so we get that. Not that it matters. Different for different theta. So how are these similar? What happened in these two situations? Yep. The r's cancelled out. So if we wanted my limit to exist, what could I have tried to arrange for?
X plus y?
Sorry?
X plus y?
X plus y instead of x times y on the top? X plus y on the bottom.
X squared plus y squared.
So you're saying that if I had just had x squared, so e.g.
Y,
So
divided by x plus y.
if you had that,
Yeah.
nice. So when we went to polar, it would have gone r cos theta, r sine theta over r cos theta plus r sine theta. And now let's see, there's only one r on the bottom, so we still get r cos theta. And that's a good candidate, because we've still got an r on the top, so that as r goes to 0, this should go to 0 as well, because it's times r. we have to be really certain of what's going on, and we are going to have to make sure that x is not equal to minus y, because otherwise the denominator is 0 and it doesn't exist at all. So this might have some really awful things happening, but this is the idea. We're left with an r on the top, and that should make the answer go to 0. But if we want to be really careful, we probably need to make sure that this thing can only be bounded inside a certain zone, which it won't be, because cos theta plus sine theta is allowed to be 0, so for certain thetas there'll be... I have a feeling this still isn't going to work, but it's got a better chance. Yeah. I have no idea. I would have to find out. I would have to try some things to see if this actually worked at all. Because I have a feeling it'll still be okay that for certain thetas, it would take a much smaller r to get close to 0 than for other thetas, but it should still be okay. I'm not sure. I'm just going to leave it like that. Pretty sure it'll work. The one I was thinking of was to do this, so that we get an r squared on the top. And everything neatly cancels. And that one will definitely work, because this thing doesn't get above 1, and so it'll be okay. Not that anyone in your exam will ask you, what does the question have to be in order for the answer to come out to this? That's a very rare thing to be asked in an exam. Though I do remember a third-year maths assignment where the question was wrong, it was a typo, and she changed the question to, what does this number have to be so that the assignment question works? But when you've only got 5 people in your course, you can do that sort of thing. Okay. I think it's a good strategy to ask yourself some what-if questions, because it helps you understand the mechanism that's going on there. We knew that it was the cancelling out of the r's that made it work. Yeah. Essentially, that's it. You usually have to be sure that the thing that's attached to the r here, or the r squared, or whatever it is, has to be bounded. You have to be able to pick a number that this is definitely less than. There's a classic Maple TA question that says, what does n have to be? And if you're really not thinking about it, you can just stick a really huge number in that spot and it'll be fine. Okay, so what was the other? IVT. All right. Well, I can say one thing about the intermediate value theorem until the recording stops, okay? Gosh, I may have to just put this under a miscellaneous instead of trying to separate it into the different categories on the Maths 1B website. So the intermediate value theorem is a theorem that relates to continuous functions, and there are several theorems that are of a similar sort of flavour in this course. There's Gall's theorem, there's the intermediate value theorem, there's the mean value theorem, and all of them tell you that a particular number exists but don't tell you what the number is. And the intermediate value theorem could have been our definition of continuity, except that it's not nearly as useful as... It makes less things continuous than I would like. But it's what our logical sense says that continuous functions should be, is that now we have to be able to state it exactly. So if f is a continuous function which sends a, b to r, then for any k between f of a and f of b, there exists, have you seen that symbol? It stands for there exists. There exists a C strictly between A and B with f of C is equal to k. That's the statement. So in shorthand, it says that if the function f achieves one value here and one value here, then it must achieve every value in between if it's continuous. So, that's so cool. Okay, sorry. The classic way of drawing it is this. Here's A, here's B, here's f of A, here's f of B. If my function goes through this point and it's continuous, then no matter what my function does, then somewhere in between it has to pass through every value between here and here, no matter what my function does. I used to bring string to these revision seminars, but I haven't got any. So no matter what my function does, if it does that, then it achieves every value between here and here quite early on. If it's a straight line, then it'll achieve every value between here and here, you know, nice lined up order. It could achieve every value between A and B multiple times, you know, a little bit here and a little bit here and a little bit here. Anything could happen, but it has to be continuous to do that. If your function has a gap in it, then it won't work necessarily. It might still work anyway. And it doesn't have to stay inside f of A to f of B. It can go up outside that zone. And that's fine because it still achieves everything from A to B somewhere. It's just really early on. So that's the intermediate value theorem. That's what it says. And so it has to achieve everything between here and here. And if I pick a specific k, then it must do it somewhere. And here is a C that produces the correct k. That's the idea. But it might happen multiple times. You know, there could be several C's that produce the correct k. Okay, and in particular, we're usually interested in one where it's below the x-axis somewhere and above the x-axis somewhere else, and it passes through everything in between. So the other way of saying it is to say if f is continuous and f of A is less than k and f of B is more than k, then there is a C between A and B with f of C equals k. This is the actual definition up here. But you can say it like this, except you also have to say it the other way around, where if the first one was more than k and the second one was less. So this one allows us to be very, you see I said k is between them, and I didn't say which order the f of A and f of B were. We didn't say which one was bigger. Yep. Okay. So most intermediate value theorem problems are about showing that some number exists. You have to usually create a new function of your own in order to use it. So either you use the intermediate value theorem to just say that your function has a zero in a particular zone, and then you use Newton's method or something to find it, or you have a brand new random problem where you have to prove that it's possible for something to happen. Do you have any in particular that you're thinking of? Yeah. Yes. Yeah, so to use it you have to say, or at least prove, or at least say it's continuous. Sometimes you have to make the function yourself.